So a good first question to answer is, what is statistics? Well, simply put, statistics is just a set of mathematical procedures for organizing, summarizing, and interpreting data. And without statistical data analysis, any observation is just speculation or superstition, not science. So in other words, without data, you're just a schmuck with an opinion. Now, even if you have no intention of going on to collect your own data through research, it's important to understand statistics because the media is really hitting you with numbers constantly. It's important to be able to unravel what all those numbers mean because, like it or not, statistics are a big part of your life. So if you can't beat them and you don't want to join them, you should at least try to understand them. So this class and methods, either psych methods or nursing methods, will essentially prepare you to be a wise consumer of research. Now, part of understanding statistics involves understanding the terminology and meaning of statistical results. So today's lecture has little to do with math and more to do with statistical terms and concepts. So really, this lecture will help set the foundation for all of the language that we are going to be using for the rest of the semester. So let's go ahead and look at a summary of the topics that will be covered in today's lecture. So the first thing that we'll talk about are populations and samples. So where do the data come from? And then the parameters and statistics that are used to describe those populations and samples. Then we'll move on to descriptive and inferential statistics and what are the differences between those two different fields of statistical analysis. And then we'll talk about something called sampling error, which is something that will be important for the whole entire semester. We'll be talking about sampling error a lot. Then we'll move on to the scientific method, which is just the basic process of how do we go from observing something to collecting data and testing a hypothesis. Then we'll talk a little bit about research designs, so the correlation, experimental, and quasi-experimental methods, which are just different ways to collect data. Each have their own strengths and weaknesses. And then I will discuss discrete and continuous variables and then the different scales of measurement. So the first thing to talk about is, where does the data in social science research come from? Or in other words, what is a population and a sample? So a population is just the complete set of scores from everyone that you're interested in. So for me as an IO psychologist, I'm typically interested in all employees, or to be more specific, all American employees. Now, if I was practicing nursing and I was conducting research, maybe I would be interested in all students doing clinicals for an RN program, for an example of a population. Just everybody that you're interested in. Now, a sample are a set of individuals that are selected from the population of interest that's intended to represent the population. So typically, the population of interest is really large and unmanageable. So for example, all American employees, that's who I'm interested in studying, probably not going to have access to all American employees. So even though typically the population of interest is too large to study, you can collect data on a sample and then extrapolate your findings from a sample to a population. So it's impossible to collect data on everyone you're interested in most cases. Part of these reasons are because, participation in research is always voluntary, and typically we're not going to have the resources necessary to reach everyone for an experiment, interview, or a survey. So again, although we may be interested in everybody from the population, we typically only have access to a subset of that population, or a sample. Luckily, collecting data on the whole population isn't necessary if we can take a sample that represents the population. So there's two major types of samples. One is a convenience sample, and that's basically when you just study whoever's available. Now, this strategy is very common in research because it's convenient, as the name implies. But the problem with this is that you're not so sure that you have a representative sample. So for example, as an IO psychologist, even though I'm interested in all American employees, maybe I only have access to students at NSC. So I could do a study on maybe the relationship between job insecurity and mental health between when I'm actually interested in all American employees, but I could just do that study with working NSC students, people that I have access to. Convenience samples can also be just within a single organization. So let's say that, for instance, a study that I did in the past we were interested from a research perspective in looking at predictors of safe behaviors in the workplace. Well, we found an organization that was a transportation agency in the Pacific Northwest that was interested in studying this within their own organization. So we went in and we collected data with these transportation employees, and we published findings trying to extrapolate what we found there to all transportation employees. And even more so, maybe to all employees in general. So we found that it's not just the organizational climate, so the banners about safety and just the general feeling about safety within the organization, but it was more important that the supervisors enacted safe behaviors and set an example. That was the biggest predictor of safety. So in that case, we had a convenient sample, people we had access to, we did the study, and then when we published it, we were trying to say, well, this may happen in all organizations, or at least all transportation organizations. So that's an example of a convenient sample. Another one, nursing students. Let's say if we couldn't study all nursing students who are doing clinicals for an RN program, maybe we just got access to students at Nevada State College. So again, convenient sample, just whoever's available, not usually representative of the population at large. Now, random samples. This is typically a more accurate representation of the population because a random sample has to meet these two conditions. So the first one, random. This requires that each individual in the population has an equal chance of being selected. So there's no bias in selection. You have widespread recruitment. Now this is easier if the population is a single organization. So for instance, let's say that I was only interested in studying this transportation agency. Well, it would be easy to get a random sample of those people that would represent the transportation agency. But if my population is all employees, then it would be harder to get a random sample from all employees, meaning that every employee, even if it was all American employees, every American employee has a chance of being selected. It's hard to have access to that population. So that's random. Just every individual in the population has an equal chance of being selected. Now, replacement requires that the sample members are selected one at a time and are allowed to be selected more than once. So a constant probability of being selected from one selection to the next is what that ensures. And when we get to the probability chapter, we'll talk more about the importance of sampling with replacement. So whenever I say that a sample is random, that means it meets both of these requirements, random and replacement. And to be a little more clear about replacement, so again, it requires that a sample member is selected one at a time and that they are put back into that population before the next selection is made. So let's go back to this picture. Let's say that this is my population and I took a random sample. So everybody in this population is available to be selected, and let's say that I select this guy first, he's in my sample, but before I make my next selection, I put him back into the population. That would be a truly random sample. So he's selected, boom, there he is in my sample. I put him back, make another selection. This guy's selected, put him back, and my population looks like this consistently for each selection. Now, if I was doing a random sample without replacement, then I would select him, and he wouldn't go back into this pool. So he would be gone for my next selection. And then I would select him, and he wouldn't be part of this population for the next selection. So that's the difference between just a random sample. So in both cases, everybody is who I'm selecting from. But with replacement, I can select the same person twice. So if I took him out, then put him back in, maybe I could select him again if it was a random, truly random sample. But if it's a random sample without replacement, I'm still selecting from all these people, but they aren't being replaced with each subsequent selection. Now, random sampling, true random sampling, is not very common in research, but it's the best way to have a representative sample. So you can randomly select from all employees from an organization or nursing programs in the United States. That would probably guarantee that you have a more representative sample if you're interested in all employees or in all students in nursing programs. Now, there are numeric values that are used to describe your populations or your samples. So a parameter is just a numeric value that describes a population. And we can only obtain this when we have access to the entire population that we are interested in. So a parameter can be a sum, so adding scores together or adding something that you're measuring together. It can be a mean, so an average of whatever you're measuring. It can be a percentage, a frequency, whatever you're measuring. It's just some sort of measure that describes a population. So for instance, the number of years at your current job for all employees, that would be a parameter. If I'm measuring, okay, how long have you been at your current organization? And I had that data for all employees. Another example would be like the percentage of missed sticks for blood draws during your first week of clinicals in an RN program for all people who have done an RN clinical or clinicals in an RN program. Those would be parameters because it describes everybody that we're interested in. Now, a statistic describes a sample. So it describes that subset of the population. And typically we work with statistics because, again, we don't have access to the population, so we don't typically have parameters at our disposal. So a statistic, just like a parameter, is a numeric value, but it describes a sample, not a population. So, for example, the number of years at your current job for all Google employees. Let's say you were trying to study how long American employees have been at their current job, but you didn't have access to all of them, but for some reason you had access to Google employees. So the Google employees would be your sample, and that number of years at their current job would be the statistic that describes that sample. Or, back to the missed blood draw sticks, let's say that you wanted to look at the percentage of missed sticks for blood draws among all RN students who are doing clinicals, but you only had access to NSC students. Well, the NSC students would be your sample, and that percentage of missed sticks for blood draws during the first week of clinicals would be your statistic describing that sample. So there are two major branches of statistical analysis. The first one is called Descriptive Statistics, and that's what we'll spend the first couple of chapters on in this class. And descriptive statistics are really just a set of mathematical procedures for organizing, summarizing, and simplifying data. Now, sometimes we have access to the entire population, and we would call those descriptive parameters if they're numbers that organize, summarize, and simplify data from a population. So here are some examples. Accident rates. So there was actually a study with 1,100 progressive insurance carriers that showed that 77% of accidents were less than or equal to 15 miles from home. So that example, since it's just coming from 11,000 progressive insurance carriers, that data came from a sample, so we would call that a descriptive statistic. Now, something that I want to point out that where statistics can be kind of misleading. You may say, oh my goodness, okay, well, most people just really drive recklessly when they're close to home. That's crazy. That many accidents coming from that close to home? Well, you have to think about how the data are collected. It's not that people drive more recklessly when they're close to home. It's that most people are, every time you leave your house, you are within 15 miles of your home. So chances are every commute that you have from home, you're going to be within 15 miles of home. That's where most people are doing their driving. So of course most of the accidents are occurring in the distance that most people are traveling. So just kind of getting you to start thinking about how sometimes a number can be misleading. So another example of descriptive data analysis would be weather. So the average rainy days in Vancouver, Washington, 167.2, which is where I spent a lot of time. Very rainy there. But here in Las Vegas area, 26 rainy days, average per year. So that average would be considered a parameter because it's describing all of the rainy days in recorded history. So that would be the population, all those days, and then the parameter would be used to describe that, so those averages. Another example would be census data. So the median household income. And you can see in Nevada it's a little bit higher than the national average, or the national median, but that would be considered a parameter, assuming that the census actually did collect data from everyone in the United States, and that everyone in the United States would be our population of interest. Another one would be IQ testing. So determining who is average, or what score is like in the 95th percentile, meaning that if you scored in the 95th percentile, then you scored better than 95% of other test takers. Now that would be considered the average of IQ. That would be considered a parameter, because typically those averages come from the entire population of test takers. Another one, in the 2012 presidential election, Romney had 47.16% of the popular vote, and Obama had 51.01% of the popular vote. That would technically be a descriptive parameter of all registered voters who actually showed up to vote. So those are just examples of descriptive statistics or parameters. Again, if it comes from a sample, like in that progressive study, then it's a descriptive statistic. If it comes from all of the data that you're interested in, or all of the people that you're interested in, then it would be called a descriptive parameter. Now, the bulk of statistical analysis isn't descriptive in nature. In research studies, typically the descriptive statistics of the sample are described somewhere in the report, just so the reader can get a sense of how representative the sample is of the population. So for instance, they'll say, 55% of our sample were male, 45% of our sample were female, our sample size was 350, average age was 26, those sorts of descriptive statistics. That's what's usually reported in the methods section of a research study. But that's not usually the heart of research. Usually inferential statistics are at the heart of a research study. And that's just when we use samples to make inferences about the population. So like I mentioned before, you typically don't have access to everybody that you're interested in. So you take a sample, you do something to them, or you collect some data, and then you use those findings to extrapolate what you would expect to see in the population if you had access to everyone in the population. So inferential statistics, just a set of mathematical procedures that are based on probability theory that allow us to study samples and make informed inferences about the population from which the sample was selected. So here are a couple of examples. So the presidential election projections, not the actual results, but all those Gallup poll findings that were reported in the news. Well, they suspected that Mitt Romney would get 46% of the popular vote, and Obama would get 49% of the popular vote. But if you actually compare that to the election results, they really underestimated both of the candidates. Now, the reason that this would be based on a sample is because they never asked me who I was going to vote for. I'm sure they probably didn't ask you either. They collected data from a sample of people and then used what they found to make predictions about what the election results would be. So another example is the president's approval rating. So in January 2014, Gallup did a poll that showed that 75% of Democrats approve of President Obama, 32% of independents approve of President Obama, and 11% of Republicans approve of President Obama. Well, again, they never asked me, probably didn't ask you. They asked a sample of 3,563 people, and then they used those findings to extrapolate what they expect to see in the population. And Gallup is really good about using random samples that are supposed to be representative of the population. And they also report their standard error, which we'll learn about for the rest of the semester. So if standard error was 5, then based on the sample, we would think that anywhere from 70 to 80% of Democrats in the population approve of President Obama. But we'll get there eventually, not today. Another couple examples of inferential statistics would be the expected lifespan of someone who eats junk food. Chances are that would come from a sample. You would have a sample of people that you would maybe survey them and ask them how often they eat junk food, and then record how old they were when they died. And you could use that sample to make predictions about how long somebody would live who eats junk food versus who doesn't in the population. So another example would be the effectiveness of medication. Chances are they're not going to be able to test this medication with everybody who has the condition that they're aiming to treat. They'll have to take a sample of people, see how the medication works with them, and then use those findings to go up for FDA approval and then eventually market the drug to everybody that has that condition. So research reports typically infer characteristics of the population, or the relationships among variables, or the effects of certain conditions or treatments from data that's observed in a sample of research participants. So again, the goal is to have a representative sample. And remember, the best way to have a representative sample is to have a random sample. Not only that, but to have a large random sample. Unfortunately, though, even random sampling is not perfect, and this imperfection is referred to as sampling error. So sampling error is just the discrepancy or amount of error between a sample statistic and a population parameter. And sample statistics almost always vary from one sample to another and between the sample and the population. So inferential statistics are not perfect, and error is pretty much always going to be there. Now, it's important to note that this error, or the difference in sample characteristics, or the difference between a sample and a population, this error is not systematic if random sampling is used. That's because we selected a random sample. It's not based on some specific characteristics such as gender. Everybody had an equal opportunity to be selected. So any differences between the sample and the population are just random errors that are due to chance. Now, if we selected cases based on gender or based on going to NSC and I have easy access to you, then you can't really be sure that the sample is representative. You might be able to attribute some of those observed differences or that sampling error to gender or them being an NSC student. So for example, maybe male employees stay in an organization longer because they're less likely to quit when their child is born. So if you took a sample of male employees and you were trying to see, okay, well, what does this sample of employees tell us about how long people typically stay at their job? Well, that might be a problem because maybe they are different than the entire population of interest if you're interested in all employees, which includes females. Or, another example, maybe male nurses have missed more sticks because they feel under pressure to perform well in a female-dominated profession. They feel like the spotlight's on them, so they have to do better. Or maybe NSC nursing students miss fewer sticks than the population at large because they get such an awesome education here. Just thinking about, if you select a sample with convenient sampling, there may be some aspect about those people that self-selected or that you had easy access to that makes them different from the population that you want them to represent. Another example is to think about participation-based research, which most research is. If you put up, a flyer saying, hey, I'm doing this study, who wants to volunteer? Well, maybe the volunteers are different from the non-volunteers, and you're actually interested in studying everyone. Your population includes everybody, but maybe those volunteers don't really represent the entire population. Luckily, we can statistically control for sampling error that's due to chance. So if we have a random sample, we'll learn about some procedures you can do to control for that random chance-based error. But if you have systematic differences that are due to some kind of bias in your sample, like selecting just males or just NSC students, or using convenient sampling, then you can't statistically control for sampling error, and that leads to some problems. So again, random sampling is optimal, whereas convenient sampling is most often used because it's convenient and it's based on who you have access to. So far, all the examples I've been making have been based on a single variable, number of missed sticks on a blood draw, or how long somebody's been at their current job. But statistics is really more than just examining a single variable. Although collecting data to examine sample characteristics is interesting, most research is really intended to better understand the laws of nature. Anything from the mating behavior of sea lions to social interaction between humans is some sort of laws of nature that can be studied with research. Now, when you start to talk about research, you usually have more than one variable. You usually have at least one independent variable and one dependent variable. Now, you've probably heard of these terms before, but these two terms are going to be very important for the rest of the semester in understanding how research studies are carried out and how we can use statistical analysis to make inferences about the laws of nature. So the independent variable is the predictor. This is the hypothesized predictor of some sort of outcome, which is the dependent variable. So the independent variable is usually what's manipulated by the researcher or the basis for different groups, whereas the dependent variable is usually what's actually measured by the researcher. Now, one way to think about these differences here, dependent, the word depend is in the name of dependent variable, and you can think, well, the dependent variable depends on the independent variable. The independent variable is what predicts changes in the dependent variable or the outcome. So here are a couple of examples of maybe, a research question that you can identify the independent and dependent variable in. So let's say you wanted to study this law of nature, that people must study information in order to learn it. Well, in this case, studying would be your independent variable and learning would be your dependent variable. We think that studying predicts learning, which is the outcome. Another example, maybe you think that different personality types have different preferences for social interaction. You think that extroverted people like social interaction more and feel more comfortable in large groups, whereas introverted people probably don't. Well, in that case, the personality types would be your independent variable, and the preferences for social interaction would be your dependent variable. So you think that personality predicts preferences for social interaction. Now, these two different types of variables are important when you talk about the scientific method. Now, that's what this flow chart represents, is the scientific method. And it's basically a tool that evolved from basic thinking processes that everyone uses. So, for example, you start off by observing something. And what's being observed is usually, your dependent variable, some outcome that you're witnessing. So, for example, let's say that I make the observation that some students perform better on statistics quizzes than others. So that's an observation. I'm observing scores on statistics quizzes. Well, the next step would be, if I was a curious person, which I am, especially as your professor, I'd be like, maybe I need to figure out what caused those differences in the statistics exams. So I'm guessing what caused it. And let's say that based on intuition, I say, I think studying improves quiz grades. Well, that leads to making an educated guess or a hypothesis. So as far as research goes, you start off with you observe something, some students perform better on statistics quizzes than others. You guess what caused it. Okay, well, just based on my intuition, I think studying is the difference there. But then once you get to making a hypothesis, you're making an educated guess, hopefully based on past research. So what does past research say? This is really where science begins. So far, this is just intuition. This is where the science begins. So I go to past research and I see that past research suggests that studying, sleep, and nutrition are all major causes of improved learning. So then I start to refine my intuition into a hypothesis and I think, okay, maybe it's not just studying. Maybe it's also sleep and nutrition. So then the next step is to collect some data. And there are different methodologies for collecting data, which we'll talk about here in a little bit. There's the correlation, the experimental, and the quasi-experimental methods. But you conduct a study and you collect some data. And then the next step is that you test your hypothesis. And just to go back a little bit, you're collecting data from a sample. You usually don't have everybody from the population. Even though you're probably interested in all students, or at least all statistics students, you're not going to have access to all those people. So you're collecting data from a sample. But then you use that data with statistical analysis to test your original hypothesis. So you could ask yourself, based on the results of statistical analysis, do those results support a relationship from studying, sleep, and or nutrition to quiz performance in this example? And then, based on that, you have a better understanding of that original observation. Even if your hypothesis isn't supported, that still results in a better understanding of what you were observing. So again, that's just the basic scientific method. And the science really begins once you start to make informed, educated guesses or hypotheses, and you start to collect data, use statistical analysis, and then interpret your findings. And just to go back, what you originally observed is your dependent variable. Then what you are hypothesizing, the cause or the predictor, that's your independent variable. Then you collect data measuring the dependent variable and test your hypothesis to have a better understanding of the relationship between your independent variable and your dependent variable. So now let's go ahead and move on to the different types of research designs that result in this data collection. So the most basic and the most frequently used methodology or research design is the correlational method. And this is when you have one group and you're just measuring at least two variables, sometimes called X and Y, and you measure those for each individual in the study. So one group measuring multiple variables within this one group. Now with this method, each person responds to the same set of questions to see how the variables relate naturally. So typically the correlational method is using survey research. So anytime that you're given a scenario and these people were administered a survey, so a single group takes a survey and then we look to see how the variables that we measured in the survey are related, that is a correlational study. So for example, is there a significant relationship between hours studying and quiz scores? Is there a significant relationship between hours slept and quiz scores? And is there a significant relationship between eating breakfast and quiz scores? Then you could see which relationship is the strongest. Now keep in mind, nothing was manipulated in those examples. We just asked people, all right, how many hours did you study for this quiz? How many hours did you sleep last night? And did you eat breakfast? And then compared that to their quiz scores. So it's a correlational study. One important thing that I really hope that you get out of this semester is that correlation does not equal causation. And this is because there's outside variables that probably contribute to the observed relationships that you see in a correlational study. So maybe students who study more also pay more attention in class. Or maybe students who eat breakfast also woke up earlier and are more alert at quiz time. So it's typically not as clear-cut as it may seem when you find a relationship between two variables. So although the correlational method is the most frequently used, it's probably the weakest design as far as trying to figure out what causes something else. Now the experimental method is the most robust methodology for research designs because we can make causal inferences. So this is when you compare two or more groups based on the manipulation of the independent variable. So the researcher changes the independent variable across groups. And this is done to show that changing the value or the level of the independent variable causes changes to occur in the dependent variable. So to accomplish this goal of having an experimental method, the researcher must satisfy these three major conditions of manipulation, control, and randomization. Now manipulation is just when the researcher manipulates the independent variable by changing its value or level from one group to another. And then the dependent variable is measured across groups to determine if the manipulation in the independent variable caused changes to occur across those different groups who got different levels of the independent variable. So here's an example of manipulation in an experimental study. So let's say that a researcher wants to study the effect of nutrition on learning. So what they do is they divide their sample into three groups. So each group receives a 20-minute lecture on descriptive statistics. Then the experimenter manipulates the independent variable. So in this case, the independent variable will be food based on nutrition. And let's say group 1 eats a Pop-Tart after the lecture, group 2 eats oatmeal and berries after the lecture, and then group 3 is the control group and they don't get any food after this 20-minute lecture on descriptive statistics. And just to be safe, let's say that each group goes to a different room to eat their respective food so that the people participating in the study don't really get wise to what's being manipulated. A little bit of deception is always a good thing. So just to recap, you have all these people, they get the same exact 20-minute lecture on descriptive statistics. Then they separate, they eat either a Pop-Tart, oatmeal and berries, or no food at all. And then they all receive a statistics quiz. And then the researcher compares the average quiz grade, the dependent variable, across all three groups. So in this case, the independent variable is what they ate, and the dependent variable is the quiz scores. And the researcher directly manipulated what these different groups ate, because they're really wanting to study the effect of nutrition on learning. That would be the first condition of an experimental study, manipulation. Now, another condition of an experimental study is control. So the researcher must exercise control over the research situation to ensure that none of the outside or extraneous factors, so anything other than food intake, is influencing the relationship between what they're interested in studying. So in other words, they want to control the scenario so that there's nothing other than nutrition, what they ate, that differs across the groups. So groups 1, 2, and 3 would all need to have an identical experience except for what they ate. So for instance, you could make sure that all participants are instructed to fast for 8 hours prior to participating in the study, just to make sure they all have the same level of hunger before you start. You also want to make sure that all participants receive the same quiz with the same instructions. They're treated the same from the experimenter, even down to they get the same room temperature in the room that they're in, or the same time of day if they don't all come in at the same time. Everything that you can possibly control that may have an influence on quiz performance should be constant across all the groups. The only thing that you want to be different is what you've manipulated, what you're interested in studying, that independent variable. So that's the second criteria for a true experiment. Now the third one is randomization. So although a random sample is preferred, meaning everybody in the population has an equal chance of being selected for your sample, it's okay if you don't have a random sample as long as you use random assignment to groups. So you don't want to say, okay, well, let's say I even used a convenient sample and the first 10 people that signed up get to be in my oatmeal and berries group, and the second 10 people that signed up are in my Pop-Tart group, and the third group, or the third group of people that signed up are in my no food group. Well, maybe the order with which people signed up for an experiment may actually have an effect on their retainment and performance on a quiz about statistics, and it's not just the food that's making that difference. So that gets at the randomization, the random assignment to groups. So you'd want to just take the whole entire pool of your sample and randomly put them into different groups. This really helps control for participant variables or individual differences, for example, when they signed up, but individual differences that may impact the observed relationship between variables. So although you want to control for the conditions that the people experience in your study, you can also control for these individual differences by randomly assigning the people in your sample to different groups. So, the people in each group are going to be different prior to manipulating any conditions. Chances are, within each group, you have differing levels of statistics knowledge, for example. But by randomly assigning your sample to conditions, you can assure that your groups are similar to each other or as equivalent as possible before you start to do any kind of experimental manipulation. So with random assignments, those participant or individual different characteristics are evenly distributed among the groups so that no group is older, smarter, more experienced, more motivated, or anything else than any other group, just by design. So that's the 3 conditions for an experimental study, which again is the only methodology that lends itself to causal inferences, saying whatever my independent variable is probably did actually cause my dependent variable. Whereas with the correlational study, you can just say there's a relationship between the two, but any causal inference isn't really warranted by that study. So then the third methodology for collecting data is a quasi-experiment. This is kind of somewhere between a correlational study and an experimental study. So it really looks like an experimental design, but it lacks random assignment. So there's a couple different types of quasi-experimental studies. One is a non-equivalent groups design, or in other words, a pre-existing groups design. This is really common, and it just uses pre-existing groups. So instead of the experimenter manipulating some sort of condition, like saying, okay, you guys get to eat a Pop-Tart and you guys get to eat oatmeal and berries, they just rely upon, okay, well, what did you eat for breakfast? We didn't manipulate it, but we're going to separate you into different groups based on what you ate for breakfast. So this is, a sample versus sample study. So let's say another example to examine the effect of lecture style on learning. Let's say that a professor teaches her morning statistics class with PowerPoint and then teaches her evening statistics class with the whiteboard. And after three class lectures, she gives them a quiz over the lecture material and compares the mean quiz score for both classes. So one group gets PowerPoint, another group gets whiteboard lectures, and then she collects data on their quiz scores and compares them. Well, this is a non-equivalent group because the morning class may be inherently different from the evening class and has nothing to do with what kind of lecture they were given. Now, another example would be the sample versus the population. So let's say that I am an HR manager at a company and I'm really advocating for on-the-job training. And I go to my employer and I say, you know, I really want to do on-the-job training. I think it's really good. The research says it is. Well, my manager may say, well, you need to do a study to make sure that it works for our employees. So before full-scale implementation of on-the-job training, I could administer on-the-job training to maybe new hires or just a small sample of employees to see if their performance evaluations are significantly higher than all the employees from last quarter, or all the employees in general. So I can compare this sample of people who received on-the-job training to the population to see if their performance is better than all the others who didn't receive on-the-job training. So those are both pre-existing groups designs. Now another example of a quasi-experiment would be a pre-test, post-test design. So this one also kind of looks like an experiment because you're manipulating something, but there really isn't random assignment because the same group is being measured twice. So this allows the researcher to control for pre-existing individual differences because the same people are being measured twice, but it's not a true experiment, again, because there's not random assignment. So let's say that we wanted to examine the effect of studying on learning. Well, I could give a group a statistics quiz and then have them study for an hour and then take the same quiz over again. That would be a pre-test, post-test design. They take the quiz, I manipulate something, the independent variable, which is I give them a chance to study, and then they take another quiz. Well, that's problematic because maybe the first quiz has an impact on the second quiz. I mean, chances are if I gave you quiz 1 in this class and then let you take it a second time, even without feedback from me, you'd do better the second time because you know what to expect. So sometimes with the pre-test, post-test design, they have two groups. One group gets the measurement of the dependent variable, in my example, the stats quiz, then the manipulation of the independent variable, in this example, studying, and then the measure of the dependent variable, again, in this example, the stats quiz. But then another group does the measurement of the dependent variable, then they don't get any manipulation of the independent variable. So in this example, they would do nothing for an hour instead of study, and then you measure the dependent variable again, and you can compare the results between those two groups to see if just taking the quiz has an impact on taking it again. So quasi-experimental, no manipulation by the researcher. It either relies on pre-existing groups or measuring the same group twice. So those are all the major research designs that are used to collect the data that you use statistical analysis to analyze and interpret. So there's two different types of variables in research. And a variable is just anything that can produce two or more different scores. Now, some variables are really easy to observe and quantify or assign a number to. So number of children, number of siblings, age, sales numbers. All those things are really easy to observe and assign a number to. But most variables of interest in psychology are qualitative in nature. Qualitative meaning they're not numerical in nature, they're more descriptive. So these are like internal characteristics that are intangible and impossible to directly observe, such as job satisfaction, intelligence, conscientiousness, those sorts of things. These are usually assessed with well-developed survey measures that assign numbers to specific responses. Now within these variables, anything that can produce two or more different scores, we have discrete and then we have continuous variables. And it's important to understand these differences because different types of variables lend themselves to different types of statistical analysis. So we'll be talking about this for the rest of the semester. Discrete variables are restricted to whole countable numbers. Another good way to think about discrete variables is how many. So some examples, how many children? That's an example of a discrete variable that's quantitative in nature. Now, Remember, I mentioned that some variables are qualitative, so they don't automatically have a number assigned to them. So you could ask somebody, what is your sex, and then assign 0 to male, 1 to female, and 2 to someone who's a hermaphrodite. I don't know. You can assign numbers to things that aren't numeric in nature. And the reason that you typically want to assign numbers to things that are inherently non-numerical is because most statistical analysis rely on your variables being measured with numbers. So discrete, whole countable numbers, another way to think about it is how many, or just numbers that can't be decimals or fractions. Now, continuous variables are not limited to a fixed set of separate indivisible categories, and they have an infinite number of possible values that fall in between two observed values. So, for example, height. So you could say, I'm 5'4", but you could be 5'4" and 2 centimeters, or anything in between 5'4" and 5'5". Most people don't break it down to that minute, number of inches or centimeters. Weight's another example. If you say you're 130 pounds, maybe you're 130 pounds and 2 ounces, or 131 pounds, or anywhere in between. Another one is, an example would be like job satisfaction. So if you ask somebody to rate themselves on job satisfaction on a scale from 1 to 7, maybe they fall in between those whole numbers that they're given to represent themselves on job satisfaction. And I'll show you an example of that here in a second. So whereas discrete variables, it's more about how many whole countable numbers. Continuous variables is all about how much. So for example, if I was measuring how many cars came through a gas station in any given hour, that would be a discrete variable. You can't have fractions of cars. But if I asked how many gallons of gas were sold in an hour, well, that would be a continuous variable because you could have decimals of gallons of gas. So let's look at the example that I mentioned earlier of measuring job satisfaction. So often the data that are collected on continuous variables, job satisfaction as an example, is in the form of a whole number response. But each whole number actually represents an interval that needs to be defined by some boundaries, or in other words, real limits. So real limits separate two adjacent scores that are located halfway between the two score or response options. Now the upper real limit is halfway above the score or response option, and the lower real limit is halfway below the score or response option. So let's say that I asked some employees, on average, I feel satisfied with my job, ... and they were given this response scale to respond to. Well, let's say that the survey participant rates themselves as a 4 for this item. So the lower real limit is a 3.5 and the upper real limit is a 4.5, halfway above, and then the lower real limit halfway below. So if they rate themselves on a 4, it could mean that they feel satisfied with their job exactly once a week. So that is accurate for them. This response scale fully captures exactly how often they feel satisfied with their job. But maybe they feel satisfied with their job more than a few times a month, but not quite once a week precisely. So they fall somewhere in between here, but they rated themselves as a 4. And it's good enough. So that's what captures that, 3.5 to 4, that lower real limit to the actual score that was measured. Maybe, they aren't satisfied more than a few times a month, but not, maybe they're satisfied more than a few times a month, but not once a week. Okay, well, on the other end of that, maybe they feel satisfied with their job less than a few times a week, but not once a week precisely. So they're somewhere in between here, and you would circle 4 anyway, even though it's not exactly once a week. Maybe it's a little more than once a week, but not quite a few times a week. So you would be anywhere between 4 and 4.5. So this is kind of an abstract example of how whole numbers can be assigned to continuous variables, and how the lower real limit and upper real limit actually represent the full range of feelings or responses that could still be considered a 4. A more straightforward example would be, how many hours did it take for you to finish the NCLEX exam? So the NCLEX exam is for people who want to become a nurse. And let's say that you're asked that question and you say, well, it took me 4 hours to finish the NCLEX exam. Well, the lower real limit would be 3.5 hours, and the upper real limit would be 4.5 hours. Because chances are it didn't take you exactly 4 hours and no minutes and no seconds to complete that exam. And the theory is that if you're asking, okay, how many hours did it take? 1, 2, 3, 4, 5, or 6 is the maximum for the RN exam. Then you're going to respond in terms of hours, but there may be some minutes in between there. So chances are, if you were around 3.5 or more, or from 3.5 to 4.5, you would say, it took me about 4 hours. Now, discrete and continuous variables have different scales of measurement. And this is the last topic that I'm going to talk about today, these different scales of measurement. So just like you need to know if a variable is discrete or continuous to determine what kind of statistical analysis is appropriate, you also need to know the scale of measurement. So data collection requires the measurement of many different types of variables, whether or not they're manipulated, and the type of statistical technique that you use to analyze it depends on this type of data. So again, it's important for you guys to be able to differentiate between these various scales of measurement. Now, these are in order of the least descriptive to the most descriptive, and you can kind of think about these like Pinot Noir, the wine, N-O-I-R, noir, in order of the least descriptive to the most. So nominal scales, you can also call them categorical. These are a set of categories that have different names and serve to label or categorize observations, but not really to make any kind of quantitative distinctions between observations. These inherently have no numeric value. We just assign numbers to them so that we can use them in data analysis. So earlier I talked about sex, so 0 being male, 1 being female, 2 being a hermaphrodite. Well, that's not meaning that males are any less than females because they had a 0 and females had a 1. It's just random, arbitrary numbers that were assigned to those categories. So marital status is another example. 0 for single, 1 for married, 2 for engaged, and as many categories as you want. The numbers don't really have any distinction or any meaning with what they're measuring. Another example would be eye color or ethnicity, just things that aren't numeric in nature that you would assign numbers to for research purposes and data analysis. So that's nominal. Now the next one is ordinal or ranking. Now ordinal scales of measurement measure the direction of the difference. So you have a set of categories that is placed in some meaningful order, so it's either ranked in terms of size or level. But the ranking doesn't indicate the magnitude of the differences between the ranks. So here's an example, tell you a little bit about me. So my top 4 shows are The Daily Show is number 1, Orange is the New Black is number 2, MasterChef is number 3, and then Pawn Stars is number 4. Now the ordering of shows doesn't really tell you how much more I like Daily Show than Orange is the New Black, or that I like MasterChef and Pawn Stars about the same. It just tells you that I like Daily Show more than Orange is the New Black, and Orange is the New Black more than MasterChef, and MasterChef more than Pawn Stars, but not how much difference is between those different ranks or ordinal rankings. Another example would be, small, medium, and large, or first place, second place, and third place. You don't really, if you just know someone finished before someone else in a race, you don't know how much time elapsed between first and second place. So again, you know the direction of the difference, first place finished before second place, but you don't know how much difference is between those two. Another one is class standing. So you know that a freshman has been attending college less than a sophomore, but you don't necessarily know how many credit hours separate any given freshman from any given sophomore. Now, the next scale of measurement is interval. Interval measures the direction and the size of the difference between different categories. So this is the same as ordinal, but each interval between categories is exactly the same size. So whereas ordinal just tells you the direction of the difference, interval tells you the direction and the magnitude of the differences between any given rating on a variable. So let's say instead of ranking my favorite TV shows, I rate my enjoyment of each TV show on a scale from 1 to 10. 1 being I absolutely can't stand it, and 10 being it's the best show on the face of the earth. And let's say I give Daily Show a 10, Orange is the New Black a 9, MasterChef a 6, and Pawn Stars a 5. Well, now you can actually compare how much I like each TV show in terms of how far apart they are in ratings of enjoyment. So some more examples would be like degrees Fahrenheit. So you know that if it's 70 degrees outside, then it's warmer than if it was 60 degrees. Well, how much warmer? It's 10 degrees warmer. So not only is it warmer, but how much warmer is it? Another example would be a golf score. So let's say that your golf score is a 2. Well, that means that you were 2 over par, and if someone else had a golf score of 0, then you had 2 more putts. Now the last one is a ratio scale of measurement. And it's very similar to an interval scale of measurement in that it measures the direction and the size or magnitude of the differences between responses. But this time it has a ratio comparison. So it has an absolute 0 point is another way to think about it. An absolute 0 point means a total absence of the variable being measured. So there's no negative values possible. So for example, how many times have you gone windsurfing? Well, if you responded 0, 0 would be an absolute absence of going windsurfing. It means you've never gone. So the existence of a true 0 point means that we can measure the absolute amount of that variable, or the distance from 0, and compare measurements in terms of ratios. So for example, someone who has gone windsurfing twice has gone 2 times more than someone who's only gone once. So some more examples: minutes needed to solve a math problem, and number of errors on a test. You can't have, a negative minutes to solve a math problem, and you can't have negative errors on a test. So going back to the interval examples, you can have a negative temperature, and you can have a negative golf score. In fact, it's a good thing to have a negative golf score. And then also, with my example of ranking favorite TV shows, that doesn't really have a true 0 point, although it can't be negative because the scale is restricted from 1 to 10. There's no way to have a true 0 point there that means an absolute lack of any kind of opinion towards that TV show. Chances are that's not going to exist. So that is the scales of measurement. I also have kind of a cheat sheet that I'll post to Canvas for you that can give you some hints on how to identify nominal, ordinal, interval, or ratio scales of measurement, because this is one of those tricky things that students seem to get hung up on in this class. So this is all I have for you for Chapter 1. I know this is a whole lot of information, and it's kind of like a foreign language with all these terms being thrown at you. But I assure you that as the semester progresses and you hear these terms more and more, they'll be more familiar to you. And really this chapter just sets the foundation for all of the things that we're going to be talking about from here on out.